All right, a very good morning to all of you, and thanks for such a pleasant introduction and inviting me for this talk. So it's always great to talk to students who have a very fresh perspective of what actually astronomy is all about. But since your most of the 2 days would be focused on building a telescope, which is what we would call optical telescope, I would want to just digress a little from there and tell you a lot about other wavelengths, which you'll probably not be building instruments for, but I really hope that someday you will take up that activity. So before we get started, I think we all understand how vast the universe is, but it's always good to go back and look at all the different length scales that we can imagine and we cannot. So I really like this interaction where here the scroll bar that you see is basically what kind of length scales that we have. We're talking about meter or so here, and these are the kind of objects that we are familiar with, right? So we have human beings, you have basketball, and you kind of get a sense of how things are. When you move your slider to the left, you'll start observing microscopic things, right? So you have cells, you have bacteria, going all the way to atoms and even beyond. But in here, we are going to the right and looking at the larger lens here, right? So you can start going of a few meters, hundreds of meters, and probably they are still there. You probably understand how big these things are. There is a football field, there is a rocket, there is a plane. But then you fast forward these things, and suddenly you are in an area which is what we call astronomy, right? So we are talking about some asteroids here. We are talking some small satellites and dwarf planets. And this is already kilometers and above, right? But it just begins, right? You can keep going up, and suddenly you are in your solar system territory. So we are talking about 10 raised to 6 to 10 raised to 7 meters. And we have Earth in that, right? So, and the smaller planets, you can keep going up, and you keep seeing bigger and bigger things. So you are basically now zooming out and looking at a larger picture. And here you see a sun, which by all means is a very generic ordinary star, but we have even giant stars, which are much, much bigger, including one of our neighboring stars here. But you don't stop there, you keep going. And suddenly at some point, you keep escaping what we call as the farthest distance that we have probed in our solar system. And then now you start to see more fascinating things. And this is where the concept of meters and kilometers stops to make sense, right? We are talking about distances which are probably hard to imagine, and we have to resort to something called light years. So are you familiar with the concept of what is a light year? Can anyone tell me that? Yes.
Distance 9,000 years.
Right. And you know how big that distance is?
3 to 10 kilometers.
Perfect. Great. Times 1 year, right? So it's a big distance, difficult to imagine. But for all astronomical purposes, I'll be using this unit. And who knows how long light takes to travel from sun? Perfect. And this is another beauty of astronomy, right? Because you are seeing light, and because it takes time to come to you, you actually are looking at the past and not at the present. So in one of our earlier speakers pointed it out, right, that this is one of the fields where we can actually see the past directly. So when you see the sun as it was 8 minutes earlier, not as it is now. You can expand this concept and look at these objects which are 1 light year. So when the light reaches you, you're actually seeing these objects as they were 1 year ago, right? And you don't stop here, you keep continue. And you are not at now light years, you are at several light years, and you'll keep going thousands of light years. And this is where we have even more interesting stuff going on, and at some point you will escape the galaxy. And our galaxy is very big. And light year is related to parsecs, right? So we are talking about some thousands of light years here, kiloparsec scales and tens of kiloparsec scales, where you'll start seeing galaxies like Milky Way and all our neighbors. And finally, you have clusters of galaxy. So galaxies are not isolated objects, most of them. They reside in galaxy clusters. And now you have reached that scale. And finally, when you go above all of this, you get to the radii of our observable universe, right? So it's a huge length scale to cover, right from objects that you see around to the most distant observable object in the universe. So we are going to take this journey and asking the questions of, first of all, what is it to see there? And how do we see it here? How do we build things so that we can probe all of this that you have just witnessed? So we'll go back to the slides now. So one of the ways you can see these things is through electromagnetic radiation. But in your time, as Professor Tarun Sauradeep mentioned, we have other means, including gravitational waves. But in this particular talk, I'll only be talking about what you can see via electromagnetic waves. So for some of you who might not be familiar with the concept, electromagnetic wave is basically a way in which you can observe very distant objects in astronomy. And the basics, as you know, we have electric field and magnetic fields which are oscillating, and they are both perpendicular to your propagation direction, right? And then you have some fundamental properties of these waves which we will be using, right? So we are talking about some things like a wavelength, which is for a wave like this, you have a distance between two successive peaks or successive troughs. And a reverse of that is what we will call frequency, right? So how many cycles of these waves happen in a single second, right? So does anyone know what's the frequency of our audio waves? Audible human frequency range? Yes? Perfect, yes. And so these are tens of hertz to 1000 hertz is kilohertz, right? Does anyone know at what frequency FM operates? Your FM stations? How many of you listen to FM? FM? No. Do you remember some numbers when you listen to Radio Mirchi? There are some numbers. 91? 93? Yeah, what are those numbers? Yes, all 90s, right? 91, 98. What are those numbers? Yes, it's the frequency of the wave, but one unit is missing, which is megahertz. So this is not 98 hertz, it's 98 megahertz. So this is basically, you have 98 megahertz means 10 raised to 6, right? Those many cycles happening per second, right? So we will be looking at frequencies or wavelengths, they are interchangeable. And that is what will characterize whether we can see it, whether we cannot see it. So you'll be making optical telescopes, right, which will be sensitive to visible light. Again, what's the wavelength of visible light? Okay, wonderful. You have all made notes. Great. Yeah. Yeah. It's great you have done homeworks. Yes. Yes. So it's nanometers. And how small nanometer is? You know meter. Meter is probably like this big. So nanometers is how many times smaller than a meter? Like, can you see nanometers? Perfect. So it's actually 10 raised to minus 9, right? So it's a billion times smaller than a meter. So we can talk in wavelengths and we can talk in frequencies. And as you can see here in electromagnetic radiation, depending on the wavelength, which we just talked about, we can categorize our entire spectrum into different names. So we have visible light, which our friend rightly pointed out is roughly a few hundred nanometers, right? And that is what we call as the visible spectrum, and all your 2 days will be focused on this part of the electromagnetic radiation, right? Which is visible, the one that we can see through our eyes. But that's not really the end of the story. I would say that's just a very small part of the story. As you go higher and higher in wavelengths, so your distance between the two peaks here is getting longer, you will start to see other parts of the electromagnetic spectrum. You will have infrared, you have microwave, and finally you have radio waves, right? You can go to the other side. If you go to smaller and smaller wavelength, you have ultraviolet, which you may have heard of, sun radiates a lot. In that you have X-rays, You must have some experience with X-rays in medical hospitals. And finally, you have gamma rays, which are the most energetic, shortest wavelength um, electromagnetic radiation. So it's a whole spectrum out there, and we can only see visible light, right? But my question to you here is, what is it that we can see in other wavelengths here? And I'll be, for example, only showing two different parts. It's impossible to cover all of this into a single hour. So of course, I am very passionate about radio, so I'll talk a little bit about that in later half of my talk. But just to contrast this, I'll also talk about X-rays, which are just on the opposite side of our visible spectrum, right? And what kinds of things we can see when we build telescopes that can actually observe these wavelengths instead of visible, right? And as I said, it's not very exotic that we have to look at these distant objects to get a feel of what these wavelengths are. Our usual devices that we have seen around actually employ these wavelengths or frequencies to achieve different purposes. As I said, X-rays are there, infrared, you have microwaves, and of course we are familiar with radio, televisions, and all of that. So it's very widely used spectrum all over the place, including your mobile phones, including televisions. But the same wavelengths we can use to explore a little bit of astronomy. And why would we need that, right? So when Galileo turned his telescope and saw Jupiter, its moons, why was there a requirement after that to be looking out elsewhere? And I cannot give an analogy better than this, which is our universe is a giant elephant. And with visible, we are only looking at one very small part of that elephant. So if you just focus yourself, these are all blind men looking at different parts of the elephant, and the one that sees the trunk says it's a snake, the one that sees the tail says it's a rope, and the one that touches the stomach says it's a wall. But it's an elephant at the end of the day, and you need all these three inputs to infer that it's actually an elephant and not be misled by just one particular thing. This is the same analogy that we would draw in multi-wavelength universe, right? So you are looking at the visible light, and visible light is great. It will show you a lot of things, but it will also not show you a lot of things. And this is where other wavelengths of this spectrum are useful in order to have a complete picture of what our universe is doing. And just to give example of that, there is a very nice visualization that I urge all of you to go and look it out for. It's called chromoscope.net. What is this object? Perfect. And has any of you actually seen this on the sky? No? Yeah, that's one of the disadvantages of being in Bangalore. The skies are not clear enough to be seeing this, but if you venture out into some areas where the sky is dark at a right time of the year, you should be able to see a part of this. And I can ensure you that would be experience of a lifetime. So this is what our galaxy looks like. This is our home, and this is the visible wavelength. And just to contrast this, if our eyes were tuned not to look at the visible wavelengths, they were tuned to look at X-ray wavelengths, what is it that you will see? Does it look anything like what you saw in the optical? And why do you think that is? Okay, so this is what I'm going to cover. Why does our universe look so different at very different wavelengths? And you can go to gamma rays, the picture will completely change, right? And then you can come this side of visible. So there are some other wavelengths like H alpha. You can go to the infrared. You can go to the microwaves, the same frequency of microwaves operate. And then you can go to radio, right? So which of this is correct? Yes. So sorry? Right. And we need all of them actually to understand what is happening, right? So now I'll get into the major part of my talk. And just like you have been interacting, I would wish this interaction continues. So at any point you have any questions, just please interrupt me and ask me, okay? So just to summarize what we saw, this is our galaxy in very different wavelengths. And I will be using wavelength and frequency interchangeably, going from the most shortest wavelength, which is gamma ray, to longest wavelength, which is radio, and visible will lie somewhere in between, which is this. All right. So the first thing, the question that I asked, why is it that our galaxy is very different at different wavelengths? And one of the major reasons for that is temperature. So let me just spend a minute or two on what I'm implying here. So what color is the sun? Is it so? What color does it look like when it's setting? Orange red. Why does it have that color? One at a time, yeah. Okay, so if you ventured out into the space, so there is no atmosphere, what color would you see? Okay, any other answers? Sorry? Our eyes. So we are looking at the visible light, like the ones that we are sensitive to. Right? Yeah, so sun emits at all wavelengths actually within the visible range, right? But there is a color where the energy that it radiates is actually maximum. It's not uniform at all the wavelengths, right? And this is one of the examples. So this might get a little technical, but don't worry if you don't understand this fully. What is shown here is how bright a certain thing is at a given wavelength. So at different wavelengths, you will have different brightness of the object. And brightness you can infer the same way you infer brightness of a flashlight or a screen, right? So sun, for example, will have its maximum brightness in the visible range. As a matter of fact, it will be somewhere around green and yellow, which is where it will radiate the maximum amount of energy. But then it doesn't stop here. It will also radiate at other places. But the maximum power will be at visible range. But that's not true for other objects. And what decides it? One of the key things that decides it is the temperature, right? So what's the temperature of the sun? At least the surface of the sun. You've all done your homework. Great. So if a body is that hot, right, it will roughly peak, it will transmit the maximum power around optical wavelengths. But what happens if a body is hotter than that? And do you know any object in the universe which is hotter than the sun? Yeah, go ahead. Sorry? Vega. What's the temperature of Vega? 9,592. Okay. Great. How did you know all my questions? Wonderful. Great. So we have hotter objects in the universe. And when that happens, the wavelength at which you will see them actually will change. So going back to the electromagnetic spectrum, if an object is around 6,000 Kelvin, which is what our sun is, you'll probably see it very strongly invisible. It's not that it's not visible in the other places, but it will strongly be visible here. But if you start increasing its temperature, right? So suppose you had a power to go to the sun and start heating it up more. You will realize that will start getting brighter in ultraviolet, in X-rays, in gamma rays. So as you increase its temperature, the maximum power that it will transmit, or the wavelength where you will see it prominently, will shift. It will become shorter and shorter. And if you start cooling it, right, you go to the sun, it's getting too hot, you want to cool it down. You start seeing the sun on the right side of the spectrum. So instead of visible, it will start radiating more in infrared, in microwave, and in radio. Right? So in some way, the wavelength at which an object is visible can also tell us a lot about the temperature of that object. Right? So for some of you who have studied blackbody radiation, they are interrelated. Right? So coming back to it, the reason that we see our universe so differently, one of the reasons is because there are lots of temperatures, right? Some things are hotter, some things are cooler. So the things that are very hot, you will probably see that for shorter wavelengths, like X-rays. X-rays are very short wavelengths. For some things which are very cold, you will see them in radio, the top part of this, right? So as the temperature increases, you will start descending down from top to bottom. So in some way, by looking at different wavelengths, you are actually monitoring a temperature. So it's like you have a thermometer and you are observing how hot or how cold things are. And you don't stop here. You then start questioning of what is heating the gas, what is cooling it, and so on and so forth. Right? So as you increase the temperature, the objects start radiating at shorter and shorter wavelength. So coming back to the multi-wavelength view, I'll now walk you through some of the pretty images, but basically to give you an idea that if you now observe the universe in X-rays, the take-home message is you are going to look at very hot objects. The temperatures can be very high. And since you mentioned the temperature of the sun, what we are talking about in X-rays is 10 raised to 6, which is a million Kelvin instead of 1,000 Kelvin. And when you look at very low temperatures, tens of Kelvin to a few Kelvins, we are looking at the radio. What is its conversion between Kelvin and degrees Celsius? Perfect. Yes. So 1 Kelvin. So there are objects in the universe that are that cold, right? So you're not talking about minus 200, minus 270 degrees Celsius. All right. So can we see all of them from Earth? Like you have heard ISRO flying satellites all the time, especially for astronomical observations. Why is that? And you have a dedicated talk maybe tomorrow. Why can't we see? Right. So why can't we see everything from the Earth? Why do we have to launch space missions? Exactly. And so what wavelengths we cannot see? Can we see visible from Earth? Can we? Okay. Yeah, we do, right? So what cannot we see is shown here. So again, this is wavelengths, and our visible light is around here. Fortunately, we're able to see things, and that's why we are building all these ground-based telescopes, including the ones that you are going to build, right? But the moment you go to shorter wavelengths, the atmosphere blocks you completely. Right? So you have to then go out and start measuring this, and that's why you see the timescales. Galileo did this hundreds of years ago, right, 1600s, but we had no clue that universe actually operated or universe had radiated in X-rays or even faint radio waves. And the reason is that we were only looking here. So in order to see the universe in other wavelengths, you have to, of course, for radio waves, you still have a window. You can do it on ground, and that's what exactly we do in our research. But for X-rays and UV, you have to fly things out. And this is where space agencies like ISRO comes in, where they can fly satellites for you. All right? So this is just a very small collection of all different facilities at different wavelengths. So in radio, for example, India has one of the leading facilities called GMRT, Giant Meter Wave Radio Telescope. This is situated in Pune, close to Pune. And if you ever get a chance, please do visit. But this is just a representative. We have a lot of such telescopes, including here we build Wasam's, Uti, there is one, and so on and so forth. Similarly, for optical, we have lots of facilities in India, including in Ladakh, Hanle. One of the first ones was here, Veni Babu Telescope near Kavalur. But then for other wavelengths, as I said, you have to really fly things out. And even for optical, you get a better sensitivity and better what we call as resolution if you go further out. And I think you have all seen Hubble pictures and how beautiful they are. So that was taken from space. India launched in 2015-16 AstroSat to observe universe in X-rays. And recently, just last year, it also launched another X-ray satellite. Does anyone know what the name of that is last year? That was for sun. It's not for X-rays. What was the first mission last year? No, it was ExpoSat. It was launched on 1st January 2023, and the payload, that was one of the X-ray telescopes looking at a very specific property. Sorry, 2024, right, last year. And that was built here by one of our colleagues here. So, and then of course we have gamma rays, we have infrared. You have probably also seen pictures of JWST, right? So it's a wide world out there, and you need all of these to have a coherent picture of what is it that universe is doing. So a quick walkthrough. We'll start with X-rays and then go to radio. Okay? Any questions till now on the fundamentals? Yes. It is. It is. So we have seen universe right from gamma rays, which are the shortest wavelengths, to radio waves, which are the longest wavelength. So you can actually build instruments, and of course you have to place them where they can see universe. And yes, you have done that. And not just that, now there are other ways to see the universe, like gravitational waves, right? Or even looking at very high energetic particles like cosmic rays. So you can map out universe in more than one way, right? But there is a lot to be done there. Any other question? All right, so now we'll just go through a gallery of different things that you see when you start making telescopes in different wavelengths, okay? So we'll start with X-rays. The first thing that you will see out there is sun, right? And sun actually radiates in X-rays too, though it is most prominent in visible light. So one of the very first mission, this was in 1949, it was launched to actually study X-ray emissions from the sun, right? And actually detected radiation. And that was the first time we came to know that there are things in the universe that actually emit X-rays, right? And then finally in 1962, so this is not really distant in the past compared to Galileo times, there was a mission launched that actually wanted to study sun because we knew that it emitted X-rays, but it started seeing other things. So very busy thing, but I'll just try to explain what it is. You have a satellite, it's scanning things around it, which is your X number of degrees that you see here. And it is recording how bright things are at these different angles, right? Which is what these points are. And suddenly started to see that in certain directions, your brightness suddenly increased, right? So you suppose you are in a dark room, your eyes are the detector, and in one particular area you see sudden a flashlight. That's exactly what they saw. So they finally said that there is evidence for X-rays from sources outside the solar system. So this is 1962, very first time we realized that universe was actually giving us a lot of information in X-rays which we could not even see ourselves. And 60s was in general a very eventful period, and I'll keep coming back to it even for radio. So long story short, from 62 to now, we are in 2025, we have a lot of telescopes with very different properties in order to study the X-ray universe better. And I just want to again remind, with X-rays, we are looking at very hot objects, right? They are the ones who will radiate very brightly in X-ray wavelengths. So Chandra was one of the groundbreaking telescopes. It was actually named after Chandrasekhar. Then, as I said, ExpoSat and AstroSat are actually Indian satellites. Both have strong contribution coming from RRI. And then recently we have XRISM, we have IXPE, NewStar. So all of these are very custom designed detectors that can actually observe the universe in X-rays. And they have told us a lot about what's going on at those high temperatures. So as I said, very first object was sun, right? And it emits, so you can ask, temperature of the sun is 6,000 Kelvin, right? And we just said that at those temperatures, you will see the sun in visible light. So what is so hot in the sun that you can see it in X-rays? Is there something hotter than the surface of the sun? The core is definitely hot, but unfortunately we can't see the core. Anything else that we can see and that's hot? Surface is 6,000 Kelvin. What happens when you come out of the surface? That's the surface, yeah. Corona, right? Are you familiar with corona? Solar corona? Yeah. Brilliant, yes. So corona extends far out compared to just the surface of the sun, which is the photosphere. And corona is very hot. It's way hotter than the sun, like the photosphere of the sun. Now, does anyone know the temperature of the corona? Sun was 6,000 Kelvin, right? The photosphere. Corona can be 1,000,000 Kelvin. It's actually one of the areas of research. What makes corona so hot? It's away from the sun, right? It's not at the surface, but it's very hot. And that's why you can see X-rays from there. Invisible, you will not see it much. Right? So that's one of the advantage, but it doesn't stop here. You have something called planetary nebulas. They're one of the most beautiful objects that you will see in the universe. So what happens with some stars, when they start getting, when they start aging, they start swelling up, and what we call as red giants. But at some point, the entire outer envelope of the red giant just blows away, right? And that's what we call planetary nebula. And they are very multi-wavelength, and also they're very hot, right? So these images that you see are all very multi-wavelength images, but the central core that you see is all X-rays, right? Because that's the hottest part of it, right? So now you can actually see the core because the rest of it has flown away. And that's very hot. You will see that in X-rays. And these are all multi-wavelength images where we have looked at optical, we have looked at X-rays, we have looked at radio, and produced some composite images, right? So this is all from NASA, a conglomeration of different telescopes. Let's move out. What happens at some point for a very massive star? They blow up. Yeah. Yeah, go ahead. It's a supernova, yes. So when stars blow up, the massive ones, they create very wide explosions, which is what we call as supernova. And because the gas is so hot, right? So you have all the material of the stars going out at a very high velocity. And this is actually going higher than the speed of the sound. So it will create what we call as shocks, right? And it will heat the gas very fast. So we'll now start seeing X-rays from these objects. And they're very symmetric, very spherical, because you have stars, entire material ejected out in a very uniform way. So these are called supernova remnants, and they can take their own time. And again, these are all multi-wavelength images, but they are also very bright in X-rays, right? So we are right now looking at solar stuff, but there are other stars which are not standalone. Our sun is like a single star, but we have a lot of these stars which are binaries. So you have two stars which are orbiting each other, okay? And a lot of fascinating things happen. It's an entire talk, but I'll just try to summarize it in one go. When you have two stars, one of it is very compact, one of it is big. When they orbit each other, the compact star starts to attract material from the other one, right? And it starts to spiral in, and it forms like what is called a disk, right? And these can be very hot again. They're called accretion disk. They can be very, very hot, and it can also change with time because the rate at which material is falling changes. So you will see a lot of these in X-rays. And a lot of our colleagues here actually work on studying these kinds of objects. So not all stars are standalone. Some of these are actually in pairs, binary systems. So it can be a lot of things, and I'll come to that. So the compact object can be a neutron star. It can also be a black hole, right? And again, how do you distinguish between the two? I'll probably come to that later. But let's move out of the galaxy. It's been enough we spent time on stars. There are some galaxies themselves that are very hot, and we call them active galactic nuclei. These are much bigger, mostly, than our typical Milky Way galaxy. So our Milky Way galaxy is not active. So are you aware about black holes at the center of the galaxy? Have you seen the images? Sagittarius A, perfect. And that's for the Milky Way. But we have a supermassive black hole at every galaxy center, right? But not all of them are active. And actually, one Milky Way black hole is not that active. But in some galaxies, you see this central black hole very active. And it does a lot of fascinating things. Without going into the detail, it can lead to production of these jets. So you have galactic plane, and you have material spewing out perpendicular to it, and that's called jets. So this image, this thing that you see is actually again X-rays, because these jets are very hot. So even not just at the stars level, but at the galaxies level, you should be able to see a lot of X-rays. And finally, the largest scales in the universe that we have is the cluster of galaxies. And again, cluster of galaxies can be very hot. So all the blue things that you see are all emitting very strongly in X-rays. And all the purple things the pink things that you see are actually strongly emitting in radio. So at the same time, by looking at two different telescopes, you can get this entire picture here. And these are massive objects, galaxy clusters, right? So you're looking at megaparsecs. It's very, very big. So all these dots that you see are actually one of like our galaxies. And then imagine within that galaxy we have solar systems and planets and then us. So that was all about X-rays. And what we saw is by building these instruments, we can study sun, we can study nebula, we can study supernova, we can study active galaxies and also galaxy clusters, right? And we are mostly looking at hot part of the universe, which are very, very hot and bright in X-rays. Now let's just shift, and in the rest part of my talk, I will focus on the other side, which is radio, right? And one of my favorites. Radio is long wavelength, right? So in terms of energy, it is low energy. It's not high energy, unlike X-rays. So X-ray can actually damage you, right? Like if you are exposed to X-rays, they can actually do damage because they are very energetic. Radio, not so much. You listen to FM every day, and FM waves are all around you. They don't damage us. They are very low energies. But at these frequencies also, you can study a lot of things in the universe. So I want to call this, our universe itself is a radio. And if you build a good enough radio station, you can actually listen to a lot of things. So let's get into that. How do we build a radio telescope? For two days, you'll be building optical telescopes. Radio telescopes look slightly different, right? Because you can't see it. So you have to first make a dish or any kind of an antenna that can receive the radio signals. Has anyone seen a radio antenna? Perfect. And what kind of antennas they are? What do you call them? Dish antennas? Those dishes, no? Wonderful. Which other antennas you have seen? TV dishes, yes.
Sir, I have seen another big one. I don't know what is it for because I passed through that way. It's very near to my home, so I guess it is for like satellite or something like that because it's very massive.
Where is this?
I've also seen it. I live next to it.
Okay.
So it's exactly like it.
Okay, and where is this? What is the area name? Electronics. Okay, okay. It's massive. Yeah, as big as this. Okay. So, for example, ISRO has a lot of these dishes to communicate with the satellites because all of this communication actually happen at radio wavelengths, right? So there might be antennas that are dedicated to those, but then you also have Akashvani kind of dishes, right? If you have passed through RT Nagar, and they also have massive dishes. So all of these are radio antennas. So you need something where you can receive the radiation. Just like in your optical telescope, you'll be doing lenses or mirrors, right? They are the ones that focus things. Here, the waves are received by the dish and they're focused right here. Okay. So now once you have received the signal, you are going to take it out to something that can boost up the power because these astronomical signals are very faint, right? So even compared to our FM stations or TV stations, the astronomical signals are very, very weak. So you need to boost their power. So we have amplifiers that can really boost the power by a factor of 100 to 1000. And finally, you need some recording device, some analysis machines to finally generate images like this, right? So that is a broader picture of how you want to create a radio telescope. So you need an antenna. It can be a dish antenna. It can be other things. You need something to boost up the power. And finally, you need some kind of an analysis to then create images and other things. All right. So again, this is all 1900s, right? Before that, we had no clue that universe was multi-wavelength. So even for radio, we only started in around 1930s. And this famous person, Karl Jansky, he was actually a communication engineer. And he was trying to build antennas to communicate across Atlantic Ocean, right? So he was in the US. He did that. And he saw that there was something unintended that he was receiving with those antennas that he had built, right? And he published this research paper called Radio Waves from Outside the Solar System. So imagine you are Karl Jansky. You have built a radio telescope. like this. And suddenly you realize that there is something that you don't expect, right? Something that's coming up from somewhere, you don't know where from. What will make you say that it is actually coming from outside and not from a FM station nearby or a digital TV next to you or a microwave next to you, right? So how do you distinguish from a system like this of what is coming to you terrestrially and what is coming to you astronomically? No, you can't. Sorry? Heat. These are very low energy, so you can't.
The pattern difference, because like if machine emits a certain pattern from our Earth, the pattern might be different compared to exoteric.
That's great. That's one way. Yeah. The frequencies. So suppose I receive something at 90 megahertz and we just realized FM operates at 90 megahertz. So there can be frequencies which are common, where our terrestrial things also emit and where our astronomical sources also emit. Then how will you distinguish? Patterns are one, and I'll come to that. Any other clues? Okay, one thing that you can look at is how is it repeating? So suppose there is a microwave next to you and you have a suspicion that this thing is what I'm seeing in my data, right? Then you can ask someone to turn on the microwave and see whether something changes, and then ask them to turn it off, see something changes. If there is a correlation between what you see and what microwave is doing, you know it's coming from microwave. Similarly, for astronomy, see at how often it's repeating, right? So if it is repeating exactly in the time when that source is coming and going, you know that this is the source that is doing this, because when it's not visible, I don't see it. When it's visible, I see it. So you can see these patterns in the data to disentangle what is coming actually from outside. And that's exactly what Karl Jansky did. And this was the first time we came to know that, yes, our universe actually radiates things in radio waves. Till now, we were only using radio waves for communications, but not for studying the universe. Then yet another gentleman, Groth-Reber, got very excited with this discovery. And he said, okay, if that is the case, I'm going to build a radio telescope and I'm going to look out what is it that is emitting this, right? And he didn't get a lot of support because no one was interested in doing this. So single-handedly, he built this antenna in his backyard, all by himself, just because he was passionate about what this was. And he literally mapped out all the emissions that he saw, and he realized it's coming from Milky Way galaxy. So this is the same galaxy that we saw earlier in radio, which is what Groth-Reber was seeing. It took him 10 years to do this, but with just sheer persistence, he was able to pinpoint all the places where the emission is coming from. And hence the field of radio astronomy started. So this is, and for 10 years, he was the only radio astronomer in the world, right? No one was really bothering. But once he released his result, people got excited that yes, there are lots of things that we can study in radio waves. His ashes are still around in a lot of radio observatories in different countries. So what kind of sources are there? Just like what we went through in X-rays, we will shortly go through radio waves also. Sun. Sun also radiates in radio. It is most prominent in visible, that's why we can see it, but it also emits a lot of radio waves. And mostly the radio waves come from corona. And that's why this question of what is heating the corona so much, why is it so much hotter than the surface, all of things can be understood if you start looking at radio waves. As a matter of fact, just 80 kilometers from here, there is a Gauribindu Radio Observatory, which is jointly hosted by RRI and IIA, and we have heliographs there to do this. Okay. This tadpole-like object is actually Jupiter. Jupiter also radiates in radio waves because it has a magnetic field. And whenever you have a magnetic field and you have energetic particles in the magnetic field, you can actually see radio waves. Milky Way. So we are just now starting from sun and we have moved out to our galaxy. Our galaxy is very bright in radio. And that's exactly what Groth-Reber saw. That's what Karl Jansky saw in 30s and 40s. That our galaxy actually has a lot of, and where is it coming from? Like what is it that is generating these radio waves? So as I said, you have magnetic fields. It's the same field that you have when you have bar magnets, right? When you generate strong enough field and you put in some electrons, right? What will electron do when it goes into a magnetic field? It will start circulating it, right? And you will study more about it in your later classes. That is what creates these radio waves. So you have huge magnetic fields and you have electrons going almost at the speed of light. And that's what creating, this is brightness not in visible light, this is brightness in radio waves, right? We have just done a false color imaging to enable you to see that, but this is all in radio. So the red things are very bright in radio and the gray things are slightly dull. And this is a more complete picture. Our galaxy is very full of features. So there are lots of features in our galaxy. All of them have been observed in radio. Someone brought up pulsars. So here they are. Pulsars are one of the objects that emit very strong radio waves. What are pulsars? Does anyone know? Yes.
So they are neutron stars which spin around their own axis and emit out charged particles.
Right. So what makes them radiate? So they are rotating very fast, right? Do you know how fast they rotate?
Sir, 6 is to power 10 in 1 second.
Yeah. So the typical number is 1,000 times a second. They are extremely fast and they are extremely small. Like we are talking about length scales of parsecs, light years, megaparsecs. These are 10 kilometers, 20 kilometers. Like a pulsar will fit a Bangalore. We don't want that. It has a giant gravitational field. But it radiates because it has a magnetic axis and a rotation axis. So it rotates, but its magnetic axis is slightly away. So when it rotates, it's like this, and there is a nice animation that I hope plays. So when it rotates, and when that radiation is in our field of view, you see it, and then it moves away, you don't see it. It's like lighthouse, right? We had no clue such an object existed in the universe till we opened our radio telescope. So this person, Jocelyn Burnell, in 60s, she was a PhD student at Cambridge, and she was basically looking at some other objects. And she started to see, when she was recording the brightness, once in a while, you have this blip, like suddenly something is coming up and going. No one knew what it was. And they were very periodic, right? So the intervals at which they came back were very, very accurate. It almost felt like it was an artificial civilization that was sending this, because nothing in astronomy was that accurate. And because we did not know existence about this, she called it little green men, right? That's what it's actually labeled as, LGM, little green men. And of course, it was unfortunately not the aliens, but it was pulsars which were newly discovered. And this discovery was actually awarded Nobel Prize. So suddenly in radio, we started to see objects like this. Recently, this is a new field emerging. The first was 2007. Another very bright object in radio literally is called fast radio burst. So you probably understand what these are. You open up your telescope on the sky and you suddenly see things flashing up and going back. They don't exist for more than a millisecond, right? So a plot like this, it was again a very accidental discovery. You were seeing something and then suddenly at a very specific time, the brightness increased and then it went down. No one knew what it was, so we called it fast radio burst. So this is in 2007. And to date, we have observed thousands of these. And still we have no clue where they are coming from, right? So we see this in different patches, like this. So all these blips that you see are fast radio bursts. They are not just in our galaxy, they are coming from outside the galaxy. They are very bright in radio wavelengths. And even when we have thousands of them, we have no clue, even now. So this started in 2007, we are in 2025, and we are still trying to understand what are they. So just like pulsars in 60s, no one had a clue, we have repeated that history by looking at this. So very much a field of research, lots of interesting things. Some, they come up and never appear again. Sometimes, some of them come again, but at a random time. Some of them periodically come back again. So it's a whole forest of objects that you can watch in radio, not knowing right now what is actually emitting this. So research is still on. Just like active galactic nuclei, which we saw in X-rays, where you have this very active black hole at the center of the galaxy, and you have these jets. These jets are very bright actually in radio. So you see all kinds of things. These are all different galaxies that have been observed in radio wavelengths. And very funny structures. This is how the galaxy interacts with its environment. And finally, the same galaxy cluster that we saw in X-rays, as I said, it has a hot gas, but it also has a lot of things which are bright in radio. So in this color, the red ones are X-rays, which are basically when you are looking at hot gas. And then these blue things are in radio. These are just radio, so you can actually contrast. And the alphabets that you see are individual galaxies. Right? So we have really zoomed out. And now we are seeing some structures which are even larger than galaxies, which are very bright in X-rays, in radios. And we are still studying them, what they are. They're called relics, but the research field is still on. Okay. Any questions till now? I'm almost at the end of my talk. Yes.
Sir, so if I click a picture or see a thing in visible spectrum, so can I convert that picture into any other spectrum?
No, because whenever you take a detector, like your optical telescope that you're going to build, it will only be sensitive to a specific wavelength, which is optical wavelength, right? So in some way, it will not respond to X-rays, it will not respond to radio waves. So in order to look for them, you need to build another detector, which will operate in those wavelengths, and they will not see optical. So you need to build different telescopes for different wavelengths.
So you mentioned that Jupiter has a strong magnetic field, so it emits radio waves. So also the Earth has magnetic field. Does it also emit radio waves?
Great question. Yes, but not as strong. You see pictures of aurora?
Yes. Yeah. They're caused by solar flares.
So the charged particles from the sun, they come, and we have a magnetic field, so they get trapped, and that's what emits those lights. And actually, they radiate in radio waves too. People have studied them in the especially polar region, because that's where you see auroras, right? But Jupiter magnetic field is orders of magnitude more strong, so you see a much stronger radio wave from there. Yeah.
So you told that X-rays is used to like see hot ones, right? So as radio is on the other side of the spectrum, is it used to see cold ones?
Yes, partly true. It does see a lot of cold objects, but it can also see hot objects. And the reason for that is, as I said, when there are very high energy or very high speed electrons in magnetic fields, they can be actually very hot, but they can also produce radio waves. So with radio, you can actually study cold objects. That is correct. But when there is a magnetic field involved, you can actually study more energetic objects.
So as we can see the sun in radio waves, so sun has a magnetic field.
Sun has an enormous magnetic field. And actually, there are a lot of people in this country that are trying to study how that magnetic field is generated, right? And that can be used to predict solar storms, right? You can monitor space weather, because our satellites get destroyed all the time because of them. So if we can predict them in advance, we can actually turn off our satellites, preserve them. So there are people who are trying to study what's the impact.
But with X-rays, we can't study for them.
With X-rays too. So in order to study solar emissions, you would probably need to study X-ray also, radio waves also, optical also, all three. So for X-rays, we have to go outside the space. For optical, you can do it on Earth. And then for radio also, you can do it on Earth. Yes.
How do we understand that the wavelengths are coming from our galaxy or other galaxies or other planets?
Great question. Anyone would want to take that up? Just a guess. So we have established that, okay, we can distinguish from terrestrial to astronomical. But then within astronomical, how do we know it's coming from our galaxy or from outside the galaxy, right? Like this is a cluster. And we see something like this. How do we know it's coming from outside our galaxy?
Sir, so if we see a particular signal and we note how much frequently is it coming,
Mhm.
so with that, can we anticipate the distance?
Only with partial success. So you can, for example, look at when things move in space, their frequency slightly changes, like Doppler effect if you have studied. So when ambulance comes to you, it's shriller. When it goes away, it's calmer. That's called Doppler effect. You can do those kinds of things, but that only will lead to a very certain stage, not after that. there are independent ways to measure distances. And I think maybe someone will cover in later talk, how do you measure distances? So for all of these, by looking at how they are emitting power at different wavelengths, you can actually estimate what the distance is. And suddenly you realize that distance is megaparsec. And you know your galaxy is only kiloparsec, so it can't come from your galaxy, right? And this was a debate. I mean, there was a very nice debate back in the 30s and 40s when people didn't know whether there were galaxies outside the Milky Way. So there is Curtin and Shapley, these two scientists, they debated that the thing that we see as Andromeda, which you may have seen images of, one team said it's in our galaxy, it's a nebula. Other team said no, it's actually a galaxy which is outside the Milky Way. And these kinds of conflicts only resolved once we started estimating distances of these objects. So distance measurement is very critical in order to say these things. Okay. Any other question? Yeah.
Yeah, so there are galaxy clusters, superclusters and all.
Yeah.
Yeah, observable universe. But outside the observable universe, since the light from there takes time and we might not even get all that light to reach to Earth before it gets destroyed.
Mm-hmm.
Get out somehow.
Right.
If we manage to. So would that mean, is there going to be any way that we can find even parts of light that come outside of our field of view of the
Yeah. It's difficult. Yeah, it's difficult. There are different ways to do that. And this brings me to the last part of my talk, which is just 2 minutes long. We had stopped at the cluster, but now since you brought up, the farthest we can go, and can we go farther than what is allowed? We'll come to the last, which is all different kinds of telescope first, right? So not one radius telescope can do everything. So you need specific kinds of telescopes, and there are lots of them, including what I said, GMRT in India. But you have all different, some of them are single telescopes, some of them are different telescopes put together, what we call as interferometers, like this, GMRT. And the list goes on and on. And square kilometer array, if you've heard about it, is coming up, and that's going to be the biggest radio telescope on Earth. But the last part that I want to cover is this, which exactly ties up with your question about how far can we see, right? And is there any way we can increase that distance? How far we can see depends on what we call as the radius of observable universe, beyond which the photons will never arrive to us, right? So that is called Hubble radius, or the radius of observable universe. But what I really want to touch upon is this. So when you look at the evolution of the universe, and I'll try to see if I can play a nice video. So this is specific to my research, so I thought I'll just spend 5 minutes doing this before we close, which is going back to distances beyond our local universe. So till now we had studied planets, stars, active galactic nuclei, galaxy clusters. But these are all in what we call in our local universe. What if we start going further out, right? So this is one of the simulations where we basically start looking at how these structures are forming. So you have Big Bang, which is basically a point which is very high density, very high temperature, and it expands. As it expands, at some point, you have these high density regions where the first galaxies have started to form. So these things, the bright objects that you see, are the first galaxies in the universe, which is what I study, and how they are forming. And as they form, of course, they also produce supernovae, and this is what you will probably see in these simulations. I'll just try to put a little back. Let's see. Yeah, so now you have more and more galaxies forming, and once in a while, you will see those flashes. Those are supernovae in our galaxies. And things have started to change, these things have started to become richer. And then finally, you will reach a stage where there is a very dense cosmic filaments and voids structure, which is what we call as large-scale structure of our universe, right? So then how do you study this? You can in radio waves. Because all of this, what is the most abundant element in the universe? Perfect. And hydrogen atoms themselves radiate in radio waves. Atomic hydrogen. Does anyone know at what frequencies the radio waves are? Not 1 meter. Uh-huh.
Let him open.
Yes, your notes. No. It's at 1.4 gigahertz. Okay, so there is a very unique radiation from hydrogen, which is at 1.4 gigahertz. And because all of these structures that you see, this is full of neutral hydrogen. Right from the Big Bang to now, we have hydrogen, right? So you can build telescopes to detect that very specific hydrogen emission, right? And with this, you can go much farther in time. Yeah.
So universe is a constant bubble which is expanding. So in that, are there smaller places which are expanding or collapsing, or is it uniformly spreading?
Perfect. So there are two kinds of things here, and this is where I think I'll also close. We are here, okay? And as we see, so till now, all my talk, I was talking about this radius, everything which is local to us. So these numbers are basically distances. So Big Bang is somewhere there, and as it comes to us, structures start to grow. So in order to answer your question, there is an expansion of the universe which is happening, and that is, sorry, cosmic expansion. Who discovered this? Hubble. That's why Hubble Space Telescope is named after him. Okay, so he looked at the galaxies and they saw the farther they were, the faster they were receding from us. And then he suddenly realized that everything is moving away from us. It's expanding. So there is an expansion, cosmic expansion rate, but not everything is flowing with that. There are these galaxies like Milky Way. They will have their own little peculiar motions. But those motions will be much smaller than the expansion. So on a broader level, everything is expanding, but they are not expanding in a frozen way. They are also doing little movements of their own. Okay. So all of these, right from our existence all the way to very close to the Big Bang, we can start studying them in radio waves by looking at this hydrogen atom, right? So by looking at the signature of this, you can build telescopes. That's what we do. We build telescopes to detect this, and then try to infer how universe has evolved from the Big Bang to today, right? Including all the structures that you saw in the earlier slides. Okay, and I think that's a nice place to stop, and I'll just leave you with a very nice conclusion from Carl Sagan, one of my favorites, that nothing is conclusive even yet. After all of this, as you saw, there are so many questions, including origins of the universe, including a lot of these interesting objects that we don't even understand properly. There is always something waiting to be known. And one of the ways you can do this is start building these telescopes. In astronomy, a lot of our knowledge has accelerated only because we have developed and built something, right? So as everyone has said, don't stop at the telescope that you'll be building in 2 days. Think about how you can be more experimental. What is it that you want to study? And how do you build instruments to study those things? So with that, I'll conclude, and if there are more questions, I'll be happy to answer.
I have a doubt regarding the X-ray. So what is the minimum temperature of an object that is required to emit X-ray?
1,000,000 Kelvin, roughly. So X-rays are also emitted by other things, but predominantly, if it has to be something in X-ray, a rough number to keep in mind is 1,000,000 Kelvin. You can sit. You can sit.
Radio telescope is recording frequencies. I mean, the galaxy is pretty big, so there are a lot of events. So how do we classify that this frequency is being emitted by this object? There are a lot.
Great. So in order to do that, you also need to have something called resolution, right? So when you build a telescope, you will also realize it has a field of view. So if you want to study minor things, you have to make your telescope to have a very narrow field of view. So you're not confused whether it's coming from this part of the sky versus the rest. So suppose if I build a telescope which covers the whole sky, I'll only get the sum total of that. So for me, it will be very difficult to tell what is coming from this galaxy, what's coming from that galaxy. But if your field of view is very narrow, right, At a given time, you're only looking at one galaxy. So then you'll be more confident in saying that whatever I'm receiving is coming from there. And in order to do that, you need to build bigger dishes. And that's why you see so many big dishes.
Sir, so as a galaxy, we know that it is spinning.
Mhm.
So if anything spins, it tends to flatten out more.
Yes.
So are our galaxies also
Yes.
spreading away from each other, like the solar systems? Are they going away from each other, or the black holes in the middle they are holding them together? Like
Yes, great question. Yes, our galaxy is spinning. As a matter of fact, our galactic structure is something like this spiral galaxy. This is another one, and this is just a contrast in what you see in radio ones versus what you see in optical. But as it spins, and again, this is a matter of research, this is spiral arms that it has. It will eventually start to merge. So it may become an elliptical galaxy. And that's why when you see elliptical galaxy, people think it's an old galaxy, right? While the younger ones are more likely to be spiral. And as they spin, they are also flatten out. So most of the galaxies only have a disk, which is very prominent. And then the rest of the things are there, but they are not as dense as the disk. And that's why when you see galaxy pictures, you will see a disk-like feature like this. So that is how they evolve. Any further questions? Okay, if not, thanks a lot for your attention. And I really enjoyed all the interactive questions and answers that you had. Thank you.